Okay, welcome back, everyone. So we will continue our discussion. So, as of now, we have studied Mamdani inference scheme for single CISO rule. So, CISO, as I pointed out, stands for single input, single output, right? So, a fuzzy if-then rule of the form if x is a, then y is b involves only one single input variable, namely x, and one single output variable, namely y. Such rules are called as CISO rules. And as of now, we only considered the case where we were given one single such rule and given an input fuzzy set A dash, we were inferring an output fuzzy set B dash. And the way we went about doing that was as follows. We computed the similarity value S between A dash and A, which was nothing but height of A dash intersection A, standard fuzzy intersection of A dash and A. And having obtained this similarity value S, we defined the membership function of B dash, our output fuzzy set, like this, right? So we essentially use the value S to modify our fuzzy set P, the consequent fuzzy set P, right? Now, consider the following case. You have a fuzzy if-then rule, but instead of having one input variable, x, you have multiple input variables, x1, x2, all the way to xn. So such a rule is called as multiple input, and we only have one output variable or one consequent variable, namely y. So therefore, multiple input, single output rule, right? So we are considering the case where we are given one or a single MISO rule, multiple input, single output rule. So this is how a MISO rule looks like. You have m input variables, x1, x2, all the way to xm, and they take values in universes capital X1, capital X2, all the way to capital Xm. And then we have output variable y, and this output variable y take values in the universe capital Y. And A1, A2, all the way to AM take values on the corresponding universes xi. So A1 is a fuzzy set over x1, A2 is a fuzzy set over x2, all the way to AM is a fuzzy set over xn. And B, of course, is the consequent fuzzy set. It is a fuzzy set over the universe capital Y. Now, here we have m input variables, right? And therefore, in order to make an inference using such a rule, using a MISO rule, you require m input fuzzy sets. In the case of single CISO rule, you had only one input variable, namely x. And therefore, in order to do inference using this rule, we only required one input fuzzy set, namely a dash. But here we have m inputs, and therefore we would require m input fuzzy sets in order to make an inference, right? So suppose you have input fuzzy sets like this, x1 equals to a1 dash, x2 equals to a2 dash, all the way to xn equals to am dash. So these are fuzzy sets over universes capital X1, capital X2, all the way to capital Xn. And we are interested in inferring an output fuzzy set, namely B dash. B dash being a fuzzy set over consequent universe capital Y. Now the question is, how do we do that? So what we will do is we will compute, we'll focus on the first part. X1 is A1. And for that, we have the input A1 dash. So we will compute the similarity value between A1 dash and A1. Similarly, if you focus on the second part of the rule, which says that X2 is A2, for that we have X2 equals to A2 dash, right? So we will compute the similarity value between A2 dash, second input fuzzy set, and the second antecedent fuzzy set. And similarly, we will go in the similar fashion until we reach the last part of the rule, last part of the antecedent part of the rule, which is xm is am. And then we will will compute the similarity value between am dash, which is the mth input fuzzy set, and am, right? So this will give you S similarity values. So like this. Now we know that in Mamdani inference, similarity is essentially computed as height of intersection. So height S1 is height of A1 dash intersection A1 all the way to SM equals to height of AM dash intersection AM. Now these SIs are local similarity values, right? Because they are obtained by focusing on specific parts of the antecedent part of the rule, right? So these are SIs are essentially local similarity values. However, to obtain the output fuzzy set B dash, we need to modify the consequent fuzzy set B. And for that, we require a single similarity value. Here we have multiple similarity values, namely S1, S2, all the way to Sm. So what do we do is we aggregate these local similarity values to produce a global similarity value. Global similarity value S. Now the question is, how do you do this aggregation? How do you combine these SIs to get S? For that, we look at the structure of the rule. It says that if x1 is a1 and if x2 is a2 and all the way to and xm is am. So we have and combining the different parts in the antecedent part of of this given rule. And corresponds to conjunction, and therefore, in order to obtain S, we essentially take minimum of S1, S2 all the way to Sm, right? So we aggregate the similarity values using minimum operation, but and essentially corresponds to a conjunction, and therefore we can use any t-norm I, but it's in the standard Mamdani inference, we use the minimum operation. So we aggregate this local similarity values SIs to obtain a global similarity value S, right? And having obtained this global similarity value, the remaining part of the inference is easy. You simply define your fuzzy set B dash in this manner. So you clip the fuzzy set B, the consequent fuzzy set B using the similarity value S. So this is something that we have already seen. So in case we are given a rule, a fuzzy if then rule, where you have multiple inputs and a single output, what do you do is given input fuzzy sets, you compute the corresponding similarity values SIs, right? And these are local in nature because they are obtained by considering specific parts of the incident part of the rule. And while having obtained this local similarity values, you aggregate them using the minimum operation or more broadly any t-norm to obtain a global similarity value S. And then you define your fuzzy set B dash, the output fuzzy set B dash like this. Okay. Now, the thing is, instead of having a MISO rule like this, if x1 is a1 and x2 is a2 and x3 is a3, so on and so forth till xm is am, we could have had if x1 is a1 or x2 is a2 or all the way to xm is am, right? So something like this. So in this particular case, our methodology is same, except the aggregation of local similarity values are done is done using the maximum operation or more broadly any T column, right? Because we have or the connective or connecting individual parts in the antecedent of the if then rule, right? And or corresponds to disjunction, and that disjunction can be mathematically realized using maximum operation or more broadly any T column. Okay. And once the aggregation of local similarity values is done, you get a global similarity value S, and then you can define your output fuzzy set B dash by clipping your by clipping your consequent fuzzy set B using this S. Oh, this should be minimum, sorry. Okay. So maximum comes into the play when you are aggregating the local similarity values. And that is, of course, obvious because when you look at the antecedent of the fuzzy if then rule, you find an or there. Okay. So let us quickly do a problem. We have a MISO rule where you have three input variables, x1, x2, x3, and we have a single output variable, namely y. So it's a MISO rule, and we are given one MISO rule. And this variables x1, x2, and x3 take values in universes x1, x2, capital X1, capital X2, and capital X3 respectively. These are finite universes, and the output, the consequent universe Y is also finite. It consists of three elements, Y1, Y2, and Y3. And this is how A1, A2, A3 are defined, and this is how B is defined. Now, given input fuzzy sets X1 equals to A1 dash, X2 equals to A2 dash, and X3 equals to A3 dash, we are required to infer an output fuzzy set B dash. Okay. And notice that this is a conjunctive form of a missive rule. Why conjunctive? Because we have an and here. We have an and here. Okay. So um, let us start by computing the individual similarity values. So what is individual similarity values? So S1 is the similarity value between A1 dash and A1, which is nothing but height of A1 dash intersection A1. So A1 looks like this, A1 dash looks like this, right? So if you compute A1 dash intersection A1, that is essentially zero point 0.5 and zero point 0.2. And so if you take the maximum, you get 0.5. Similarly, S2 is height of A2 dash intersection A2. This is A2 dash, this is A2. If you take the intersection, what will you get? 0 0.1, 0 0.7, 0 0.3, 0 0.1, 0 0.7, and 0 0.3, and therefore height would be, oh my God. Unfortunately, what I had written is lost thanks to the amazing services of Microsoft. Anyways, okay. So S1 was height of A1 dash intersection A1. A1 dash is this, A1 is this. If you compute the intersection, what will be the membership value? 0.5 and zero point 0.2, maximum is 0.5. S2 is height of A2 dash intersection A2. What is A2 dash intersection A2? The values would be 0.1, comma 0.7, comma zero point 0.3. So height would be 0.7. S3 is height of A3 dash intersection A3. What would be A3 dash intersection A3? 0.2, comma 0.7, and therefore their height would be 0.7. Okay, so this should have been x31, x32, and this should have been x31 and x32. Okay, so we have computed the individual, the local similarity values. In order to obtain the global similarity value, we essentially take the minimum of all of them because the given MISO rule is conjunctive in nature. It consists of and. So if you take the minimum of 0.5, 0.7, and 0.7, you'll get 0.5. And what would be mu b dash of y? It would be minimum of 0.5, comma mu b of y, right? And therefore, how will your b dash, this fuzzy set b dash, the output fuzzy set b dash look like? You'll have to take minimum with 0.5 of membership value. So minimum of 0.5 and 0.5 is again 0.5 only. Minimum of 0.3 and 0.5 is 0.3. Minimum of 0.5 and 0.7 is 0.5. So this is your output. Again, nothing very complicated. Just compute the similarity values. Similarity values are very straightforward to compute. Simply height of AI intersection AI. Having computed the similarity values, aggregate them, and then clip the fuzzy set B in order to get B dash. Now, suppose instead of having a conjunctive Miso rule, you had a disjunctive Miso rule. That is, instead of and, you had or. So, what would have been the global similarity value? In that case, we should take the maximum of this local similarity values. And what will be maximum of 0.5, 0.7, and zero point 0.7? It would be 0.7. And therefore, your output fuzzy set B dash would be obtained by taking maximum of zero point 0.7 with membership values of B. What is the maximum of 0.5 and zero point 0.7? It is, of course, 0 0.7. What is maximum of 0.3 and 0.7? Is 0.7. And what is maximum of 0.7 and 0.7? It's again 0.7. Okay, so this is your output fuzzy set using Mamdani inference scheme. Now, we have saw the situation where we had a single MISO rule, right? A single CISO rule, sorry. In fact, this is what formed the greater part of our discussion of previous session, of previous parts of the session. And then we considered the case when we had a single MISO rule. In this case, you find out the local similarity values, and then you aggregate them to obtain a global similarity value. Now we will consider the case when we have multiple rules. That is, you have a multiple CISO rules and multiple MISO rules. Okay, so let us start with multiple CISO rules. Suppose you have a rule base of n if-then rules, and those n if-then rules are CISO rules. So if x1 is a1, then y is b1. If x is a1, then y is b1. If x is a2, then y is b2. All the way to if x is an, then y is bn. And here your antecedent variable is x, consequent variable is y. They take values in universes capital X and capital Y respectively. And this fuzzy sets a1, a2, a3 all the way to an. These are fuzzy sets over the antecedent universe X, and b1, b2 all the way to bn. These are fuzzy sets over the consequent universe Y, capital Y. Okay. Now notice that each rule in this rule base consists of one input variable, namely x. And therefore, to be able to do inference in this setting, we should be given a input fuzzy set A dash, right? And using these rules, we will produce an output fuzzy set B dash. Here, there is only one input variable, and therefore we would be required, we would need a single input fuzzy set A dash to do inference. This has to be contrasted with the MISO rule, where you had multiple input variables, and therefore you had to be given multiple input fuzzy sets in order to do inference. Here we have a single input variable, and therefore we only want a single input fuzzy set A dash in order to do the inference. Suppose you are given x equals to A dash, and we want to infer the output fuzzy set B dash. How do we do that? So the philosophy is this: we have n rules, right? And each of these rules is a CISO rule. We can consider these n rules individually. Okay, so we'll start with first rule, then we will go to the second rule, all the way to the nth rule. And for each of those n rules, we know how to do the inference. If we simply consider the first rule, then we will compute the similarity value S1. That would be height of A dash intersection A1. And using this S1, we can get the output B1 dash as minimum of S1 comma B1. So if we just consider the first rule, we know how to get an output fuzzy set. Similarly, if you just consider the second rule, you know how to obtain the output fuzzy set B2 dash. Similarly, by considering the nth rule, you can get a output fuzzy set Bn dash. Having obtained this individual output fuzzy sets B1 dash, B2 dash, all the way to Bn dash, you simply aggregate the output fuzzy sets to produce one single output, namely B dash. Okay, that is for each rule I, you compute the similarity value Si, which is nothing but height of A dash intersection Ai. Having obtained the similarity value Si, you obtain the corresponding output fuzzy set Bi dash. Okay, so you have n local output fuzzy sets B1 dash, B2 dash, all the way to Bn dash. And now we want to aggregate this output fuzzy sets Bi dash to obtain one output fuzzy set B dash. And how do we do that? We use a aggregation operation G. Now G generally is taken to be maximum or minimum, but in general it can be any associative operation, right? And why associative? Because you need a way to extend. So if we had just two rules, then we would have gotten two fuzzy sets B1 dash and B2 dash. And then we aggregate this using an operation G, a binary operation on the unit interval. Then your output fuzzy set B dash is obtained by aggregating B1 dash and B2 dash using G. That is the membership function of B looks like this. So you compute the membership function of B1 dash and B2 dash at Y, and then you basically apply G to it to obtain a single value. Right? So this is what it means to aggregate B1 dash and B2 dash using operation G. But what if we had three rules instead of two rules? Or what if we had four rules or five rules? Therefore, we need a system, we need a well-defined way to apply G to more than two arguments. And that is what associativity allows us to do. What exactly associativity brings to table? It brings to the table a well-defined way to extend any binary operation to an array operation. So given x1, x2, xn, we can define this the value of G at x1, x2, xn in many ways, right? You can say that you first suppose I have three variables. Let's take the specific case. So G is a function from, it's a binary operation on 0, 1, right? So it takes two numbers in 0, 1 and it produces another number in 0, 1. Now we were interested in extending this G to three arguments. So we'll take x1, x2, and x3 in 0, 1, and let us see what are the possible ways of defining G x1, x2, x3. We can say that you first compute the last two arguments x2 and x3 using G, and whatever you get, you then compute G on that. So G of x1 comma G of x2 x3. Another way would be you first compute the first two arguments and then compute the last argument. Now these two are two different ways of defining G on three arguments, right? And they could be different, but the moment G becomes associative, these two are equal. If G is associative. Similarly, when you have four arguments, then you have many ways of defining this G. You can first evaluate the first three arguments and then apply it with the last argument. Or you can do this, right? And there are two ways of defining this and this. So altogether, we have four ways of defining G on basically x1, x2, x3, x4. Now, if G becomes associative, then all those definitions become equal. So long story short, associativity allows you to extend a binary operation on a set to an array operation on that set in a well-defined manner, right? So that is why you require this operation G, using which you are aggregating the local output fuzzy sets B1 dash, B2 dash, all the way to Bn dash to be an associative operation. And the prototypical associative operations are maximum or minimum, right? So in generally in questions, you will be uh, specified what operation is to be used in order to combine the consequent fuzzy sets. Okay. So let us quickly do a problem. We have again three seesaw rules. Okay. And the input variable is x, or the antecedent variable is x, and the consequent variable is y, and they take value in universes capital X and capital Y respectively. And these are the individual fuzzy sets AIs, and these are fuzzy sets BIs. And given this particular input x equals to a dash, we are required to infer output y equals to b dash using Mamdani inference scheme, and we are given that you use maximum for aggregation, right? So use maximum for aggregation of consequent fuzzy sets, right? So I hope that was implied, but in case you were confused, I will be more specific. Use maximum for aggregation of consequent fuzzy sets. Okay, so let us quickly infer the individual output fuzzy sets B1 dash, B2 dash, and B3 dash. So for that, we have to compute the similarity values. Similarity value S1 is height of A dash intersection A1. So this is A1 and this is A dash. So what is A dash intersection A1? This is 0.2, and then you have 0.7, and therefore this is 0.7. Similarly, so 0.2, because minimum of 0.8 and 0.2 is 0.2, minimum of 0.5 is, what is the maximum? This is 0.5. 0.1, because minimum of 0.2, 0.1 and 0.2 is zero point 0.1, and minimum of 1 and 0.7 is 0.7, so therefore 0.7, right? And therefore B1 dash is obtained by taking minimum of zero point 0.7 with membership values of B1, right? So minimum of zero point 0.7 and zero point 0.2 is zero point 0.2. Minimum of zero point 0.7 and zero point 0.5 is again 0.5. Minimum of 0.7 and zero point 0.3 is 0.3. Now, the similarity value corresponding to the second rule is zero point 0.5. Therefore, B2 dash is obtained by taking minimum of 0.2 with the membership values of B2. So minimum of 0.5 and 0.1 is 0.1, minimum of 0.5 and 0.8 is 0.5, and minimum of 0.5 and with 0.8 is again 0.5. And lastly, I'll compute B3 dash. The similarity value corresponding to the third rule, that is S3, is 0.7. Therefore, B3 dash is obtained by taking minimum of 0.7 with the membership value of the set B3. So minimum of 0.7 and 0.9 is 0.7. Minimum of 0.7 and 0.9 is again 0.7. And minimum of 0.7 and 2 is 0.2. So we have obtained the individual local output fuzzy sets B1 dash, B2 dash, and B3 dash. Now we will obtain the output fuzzy set B dash by aggregating this B1 dash and B2 dash and B3 dash. And the question already specified that we are required to take use the maximum operation for the aggregation. So the membership of Y1 in this B dash is maximum of membership of Y1 in B1 dash, B2 dash, and B3 dash. And what is that maximum? It's 0.7. I hope that is clear. Maximum of 0.2, 0.1, and 0.5 is 0.7. Similarly, membership of Y2 in B dash is maximum of membership values of Y2 in B1 dash, B2 dash, and B3 dash. And that again is 0.7. And similarly, you can compute the membership of Y3 in B dash, which is maximum of 0.3, 0.5, and 0.2, and therefore it's 0.5. So this is your output, final output, right? Again, nothing very complicated. Moving on. So let's do another question. If temperature is warm, then fan speed should be high. If temperature is moderate, then fan speed should be medium. If temperature is low, then fan speed should be extremely slow. So warm, moderate, and low are defined as fuzzy sets over this universe. So your antecedent universe is this, and this is your uh, antecedent fuzzy sets A1, this is A2, and this is A3, right? So this is A1, this is A2, and this is A3. And what are the consequent fuzzy sets? High is your B1, this is B2, and B3 is extremely slow. So B1 is high, B2 is medium, and notice that the B3 is extremely slow, right? So, and what we are given is slow. So extremely is a hedge, right? And therefore we know we have already seen how to obtain the membership function of extremely slow, or in that matter, extremely F, where F is a fuzzy set. And that is obtained using the cube operation, right? So extremely is a hedge. And the widely accepted way to model this linguistic hedge extremely is this, right? So our consequent fuzzy set, just a minute. Okay, so our consequent fuzzy set B3 is not slow but extremely slow, right? So this is basically a slow cube, if you will. Okay, we are given the the value of input value, the value of input variable temperature as 12 degrees centigrade, and we're required to infer the fan speed using Mamdani inference scheme using center of maxima method. Okay, and notice that nothing is specified, right, as to how we need to aggregate the output fuzzy sets B1 dash, B2 dash, and B3 dash. So use maximum operation in such a case. Okay. So let us start by getting a sense of how A1, A2, and A3 looks. So A1 is this, right? A2 is this. So A1 is warm. This is moderate. And this is low. These are fuzzy sets over the universe, minus 20 to 50 degrees centigrade. And this is our output fuzzy sets. So this is, of course, your output fuzzy set B1 high. And this is B2, which is medium. And these are fuzzy sets over. And this is basically the fuzzy set corresponding to slow. However, B3 is extremely slow, right? So you will apply the cube operation on the membership function of slow. And when you do that, you end up getting this. So this is B3, right? This is B2, this is B1, this is A1, this is A2, and A3. So now we have plotted the all the antecedent fuzzy sets A1, A2, and A3, and all the consequent fuzzy sets, namely B1, B2, and B3. And our input is given to be 12 degrees centigrade. So that is x1, sorry, input x variable is equals to 12. So we start by computing the individual similarity values. So S1 is Now notice the in we are given, instead of being given a fuzzy set as an input, we are given a particular value. So what we will do in such a case, we will do fuzzification. Nothing is given, so we perform the singleton fuzzification, right? So similarity value of the singleton, suppose this is your input value, right? This is what is given to us. You perform singleton fuzzification to get ADAS, right? And ADAS has this membership function that it is 1 if x is equals to 12, and everywhere it is 0, right? And when you compute the similarity value of A dash with A1, we have already seen that it turns out to be equal to the value of membership function of A1 at 12. Again, this I have already done when I talked about fuzzification and defuzzification, and I did a model problem on that. And there I illustrated that when you are doing singleton fuzzification of an input variable, then computing its the similarity value of A dash, the fuzzified input, with A is fairly straightforward, right? And this is how uh, you do that. This is basically what you end up getting, right? So in case you are having difficulty understanding why similarity value S1 is basically the membership of 12 in the fuzzy set A1, I would encourage you to go back and watch the explanation of those slides carefully, right? And I'm not going to mention this again and again, right? And from now on, I will write the similarity value without any explanation, assuming that you are already familiar that when you are doing singleton classification of input, things are pretty straightforward. So A1 is our fuzzy set. A1 is this fuzzy set, right? And what is the membership of 12 in this fuzzy set? So 12 lies somewhere here, and it belongs to green fuzzy set, namely A1 fuzzy sets to membership 0. So S1 is 0. Similarly, S2. The similarity value of A dash with A2 is nothing but the membership of 12 in A2. Now again, 12 lies somewhere here, and this is A2, right? So this is A2. So this is basically, this is your similarity value. So let us quickly compute that similarity value. So A2 was what? It was 5, 15, 25, 35. So this is nothing but x minus 5 divided by 15 minus 5 evaluated at 12. So 12 minus 5 is 7, 15 minus 5 is 10, so you get zero point 0.7. Similarly, x3 is a3 12, a3 is this, 12 again is here. Therefore, what will be the similarity value? A3 is minus 20, minus 25, 50. So this is nothing but 15 minus x divided by 15 minus 5 evaluated at 12. So 15 minus 12 is 3, 3 divided by 10, so this is 0.3. So S1 is 0, S2 is 0.7, and S3 is 0.3. So S1 is 0, right? And this is basically our A1. So how will we obtain A1 dash, B1 dash? Sorry, this is not A1, right? Just a minute. Okay, turns out that these slides are incorrect. But okay, that's nothing to be worried about. We can simply uh, do things here. So this is our B1, this is our B2, and this is our B3. So our first similarity value turns out to be 0, right? And B1 dash, and therefore your first output fuzzy set B1 dash is identically 0, or in other words, it's the empty set basically, right? So when you clip this B1 using 0, you basically get the horizontal axis. Similarly, what would be B2 dash? It would be minimum of S2. S2 in this case is 0.7, and this will be your output fuzzy set B2 dash. So 0.7 is gonna lie here, right? And when you clip your B2 with 0.7, you get this, right? And B3 dash is minimum of S3, which is 0.3. Now 0.3 is here. So if you clip your fuzzy set B3 using 0.3, this is what you will get. Right? Now we want to obtain the final output B dash, which is nothing but maximum of B1 dash, B2 dash, and B3 dash. So we are taking maximum of these three clipped fuzzy sets. And when you do that, what will you get? You will get this. So this is output fuzzy set B dash, the one that is shown in red. So the area, the region subtended by the membership function of B dash with the horizontal axis is this, right? So what is the height of this fuzzy set B dash? It's definitely 0.7, right? And what is the set M? Basically the set of values of the universe capital Y where that height is attained. It is, say this is A and this is B, right? So this is A, and therefore your output would be A plus B by 2, since we are required to use center of maxima method for defuzzification. And this A and B can be figured out pretty easily. All you have to do is solve y equals to 0.7. Sorry, this is denoting the y-axis and this is denoting the z-axis. So I should be a bit careful here. The z equals to 0.7. And for A, we will solve z equals to, so what is the equation for B2? It's 200, 250, 350, 400. So Z1 would, Z it should be y minus 200 divided by 50. So when you solve this, zero point 0.7 equals to y minus 200 by 50, you will get A. And when you solve Z equals to 0.7 with Z equals to 400 minus y divided by 50, when you solve this, you get B. So let us do that. So A equals to 200 plus 0.7 multiplied by 50. So that's 7 times 5 or 35. So this is 235. And what is B? B is 400 minus 0.7 times 50, which is 7 times 5 only, and that is 30. So 400 minus 30 is 370. 370 minus 5 is 365. So therefore, A plus B by 2 is sum of these two. So what is the sum of 235 plus 365? It's 10, 6, 3, 9, 10, carry 1, 3, 2, 5, 6. So I hope I'm not committing an error. I am not. 3, 300. Okay. And it was actually very clear by looking at this only. So a plus b by 2 is going to lie in the middle. So that was evidently 300, but I thought that I should do the calculations to give you a flavor. So the output is equals to 300 RPM. Okay. So take some time, recognize what I have done, and convince yourself that you know this is what you are required to do when Mamdani inference has to be performed. Okay. So these slides are actually incorrect. I should have been a bit careful, but anyways, I did everything by my own. Okay. Now, lastly, we have the case when we have multiple MISO rules. So you have multiple input and single output rules, and you have many such rules, right? So this is probably the most I won't say complicated case, but certainly not so straightforward, right? So the first rule is if x1 is a11 and x2 is a12, all the way to xm is a1m, then y is b1. Similarly, if x2 is a21 and x2 is a22, all the way to xm is a2m, then y is b2. All the way to x1 is an1 and x2 is an2 and xm is am, then y is bn. Okay, where variables this x1, x2, all the way to xm, these are in antecedent variables, and they take values in universes capital X1, capital X2, all the way to capital Xm. And the output, the consequent variable is y. This take values in universe capital Y, and this sets a11, so a11, a21, all the way to an1. This so a11, a21. These are fuzzy sets over the first antecedent universe. Similarly, a2, a12, a22, all the way to a and 2 are fuzzy sets over the second antecedent universe. And similarly, an1, an2, all the way to a and m are fuzzy sets over the last antecedent universe, namely xm. So in other words, ai is a fuzzy set over xj for all I and j, right? And bi is of course is a fuzzy set over the consequent universe y, right? So this is the setup, right? Take some time and digest this. Now, we have multiple input variables, right? Therefore, in order for us to do any kind of inference, we require multiple input fuzzy sets. And how many fuzzy sets we require as inputs? We require m fuzzy sets because we have n input variables. So given these input fuzzy sets, x1 equals to a1 dash, x2 equals to a2 dash, all the way to xm equals to am dash, we are required to produce an output fuzzy set b dash. Again, the philosophy is same. We can consider each of these m each of this n MISO rule in isolation, and we already know how to deal with a single MISO rule. Using that, we can obtain a output fuzzy set b1 dash, and similarly b2 dash, and all the way to bn dash, and then we will aggregate all those uh, local output fuzzy sets to obtain the final output fuzzy set, namely b dash. That is for each rule I between 1 and n. So for each rule, you infer the bi dash. And how we will do that? So this is a MISO rule. So in order to deal with the MISO rule, we first compute the local similarity values and then we aggregate them. And the kind of aggregation depends upon the kind of rule we are dealing with. This is a rule base where each rule is conjunctive MISO rule because we have and here. So having computed the individual similarity values, we aggregate them using minimum, right? Okay, that's what I'm doing. Again, since we have multiple rules, so we have two indices I and j, and that can be a tad bit confusing. But if you closely follow what I've written, things would become apparent. I'm considering the ith rule, right? So first compute the, let us compute the, so when we are dealing with ith rule, our similarity values will be si1, si2, all the way to sim, right? Because we have to compute m similarity values since we have m input variables. How will we compute si1? It is nothing but height of the ith input fuzzy set which in this case happens to be the first input fuzzy set, sorry, A1 dash with the first antecedent fuzzy set in the ith row. So that is AI1. Similarly, what is this? This is the height of second input fuzzy set. So A2 dash with the second antecedent fuzzy set in the ith row. So you get I2. On it, similarly, this is height of AM dash, basically AM dash, the mth input fuzzy set with the mth antecedent fuzzy set in the ith row. So this, okay. So talking about this machinery in abstract is a bit confusing, but you will see that when we do an actual problem, things are not very complicated. Okay. So you consider each meso rule in isolation, infer the output fuzzy set bi dash, and finally you aggregate this output fuzzy, this local output fuzzy sets to obtain the final output, which is b dash. And again, that is done using an associative operation, generally maximum or minimum. Nothing is specified, then we'll use maximum. Okay. So I hope the philosophy is clear. Whenever we have a rule base in which we have multiple CISO rule or multiple MISO rule, we deal with each rule individually and infer a local output fuzzy sets. And we do that for all the rules in our rule base. And that give us a bunch of local output fuzzy sets. And we aggregate those output fuzzy sets to obtain the final output. And this aggregation is done using an associative operation G, generally maximum. Okay. So let us do a question to clarify, to make the discussion that we have had so far a bit concrete. We have three MISO rules, and we have in each rule we have two input variables x1 and x2. Okay, and we have of course our output variable y. It take values in universe capital Y, and these are the output. These are consequent fuzzy sets b1, b2, and b3. So I've specified these sets aij using a table. Okay. So A11, A21, and A31, these are fuzzy sets over universe X1. And similarly, A12, A22, and A32 are fuzzy sets over X2. Okay. So, and this is how their membership values look like. Okay. So this is A11, A21, and A31. And this is A21, A22, A23. Okay. And we are given input x equals to a1 dash and x equals to a2 dash. These are fuzzy sets over x1 and x2 respectively. And we're required to infer the output fuzzy set b dash using Mamdani inference. And of course, the aggregation has to be done by the maximum operation. Aggregation of local output fuzzy sets. Remember, aggregation of similarity values is done using minimum or maximum depending on what kind of rule you are dealing with. Either it is a conjunctive rule or a disjunctive rule. So that you have, that decision is something that you need to take yourself by looking at the rule. However, the aggregation of output fuzzy sets is something where you have freedom, and therefore an external piece of information needs to be supplied. Okay, and that is what this does. And this is our input fuzzy set A dash, A1 dash, and this is our input fuzzy set A2 dash. Okay, so let us compute the similarity values first. So this is for first rule, this is for second rule, and this is for third rule. Okay. So what is S11? It is the similarity value between A1 dash and A11. Okay. So we are considering the first rule. So we will compute the similarity of A1 dash with A11. And then we will do the similarity value of A2 dash with A12. Okay. So I will write this here. Now, what is the similarity value? So it's the height of A1 dash intersection A11. So this is A1 dash and this is A1. So if you compute their intersection, what will you get? You will get for X11, the membership would be minimum of 0.4 and 0.3. So 0.3. And what would be the membership of X12? It will be minimum of zero point 0.1 and 0.7. When you take the max, and what kind of aggregation needs to be done for similarity values? Conjunctive aggregation or aggregation using minimum, because we have and here. Okay. And therefore, this is basically um, okay. So height of A1 intersection A1 dash intersection A11. So it's basically 0.7, right? I hope I am not committing any mistake. I am. So this is 0.3. Okay. So this is A1 dash, this is A11. So I compute their intersection. What would be the membership of X11 in this intersection? It would be minimum of 0.4 and 0.3, which is 0.3. And what would be the membership of X12? It would be minimum of 0.1 and 0.7, which is 0.1. And when you take the maximum, you get 0.3, right? Now, similarly, let us compute the similarity value S12, which is the similarity value between A2 dash and A12. So this is A2 dash and this is A12. So what is so that is the height of A2 dash intersection A12. So what is the membership of X11, X21 in this intersection? This is minimum of 0.5 and 0.1. So this is, where do I write this? Maybe here. Minimum of 0.5 and 0.1 is basically 0.1. Minimum of 0.8 and 0.1 is again 0.1, and minimum of 0.9, 0.2 is 0.2. And what is the maximum of all these things? It's 0.2. Now, similarly, we'll compute S21. So we will compute the similarity value between A1 dash and A21. Okay. So now we are considering the second rule. So this is A1 dash and this is A2 dash. So what is the membership value of X11 in that intersection? It is minimum of 0.6 and 0.3. So again 0.3. And what is the membership of X12 in that intersection? It is minimum of 0.2 and 0.7. So again 0.2. So this is 0.3, right? Because we are interested in height. Now you do all the computations in a similar manner, and this is what you will get. Okay. I'm skipping the going through going through the explicit calculation in interest of time. So these are local similarity values for the three rules. Now, by looking at the rule, we realize that we have an and connecting different pieces in the antecedent of the rules, and therefore, in order to obtain the global similarity value for each rule, we will do the minimum. So, what is minimum of 0.3 and 0.2? It is 0.2. What is minimum of 0.3 and 0.2? Again 0.2. And what is the minimum of uh, this 0.7 and sorry 0.7 and 0.2? This is again 0.2, right? And therefore, we have 0.2, 0.2, and 0.2. Now let us compute the fuzzy sets B1 dash, B2 dash, and B3 dash. How will be B1 dash given? It is minimum of S1, comma B1, or in other words, minimum of 0.2, comma B1. This is how our B1 looks. So in order to obtain B1 dash, we'll take minimum with 0.2 of different membership values of B1. So 0.1, 0.2, 0.2, right? Because minimum of 0.1 and 0.2 is 0.1, minimum of zero point 0.4 and 0.2 is 0.2, minimum of 0.9 and 0.2 is again 0.2. Now what will be B2 dash? It will be minimum of S2 comma B2. What is S2? It's 0.2 only. So we again do that and it turns out that this is entire 0.2. And what is B3 dash? It is minimum of S3, which again happens to be zero point 0.2, and this is B3. And when you take the minimum of 0.2 with 0.5, 0.5, 0.3, you again get 0.2, 0.2, 0.2, right? So you have computed the individual output fuzzy sets, B1 dash, B2 dash, and B3 dash. Having done that, let us now compute the final output, which is B dash, which we will do by aggregating this B1 dash, B2, and B3 dash using the minimum operation. In other words, in this case, it is very clear that this is 0.2, right? So basically, we need to take maximum row wise. So our output fuzzy set B dash is very simple in the sense that it has membership value 2 throughout. So this is basically our output fuzzy set given input x1 equals to a1 dash and x2 equals to a2 dash. Okay. Now, instead of having a rule base of multiple CISO rules where you had and appearing between parts of antecedent between different parts of the antecedent of the rules, you could have a or. So instead of x1 is a11 and x2 is a12, you could have x1 is a11 or x1 is a2, right? So this is basically a disjunctive MISO rule. Why disjunctive? Because you have disjunction between x1 is a11 and x2 is a12. You don't have an and, you have an or. So in this case, the only difference is going to be how we aggregate the local similarity values. So instead of having minimum here, you will have maximum. Everything else stays the same. You infer the individual, the local output fuzzy sets B1 dash, B2 dash, B3 dash, and then you aggregate them to obtain your final output fuzzy set B, right? So let's do the same problem, but here we have disjunctive MISO rules instead of having conjunctive ones. So we have or here. Okay. So we have already computed these values. These were 0.3, 0.3, 0.7, and 0.22, 0.22, 0.2, sorry, 0.2, 0.2, and zero point 0.2. Now, since we have an or here, the global similarity value for each rule would be obtained by taking maximum of individual local similarity value. The maximum of 0.3 and zero point 0.2 is 0.3. Maximum of 0.3 and zero point 0.2 is again 0.3. Maximum of 0.7 and zero point 0.2 is 0.7. Right? So we have 0.3, 0.3, and zero point 0.7. Okay. Now so B1 dash is minimum of S1 comma B1 or minimum of 0.3 comma B1. B2 dash is minimum of S2 comma B2 or minimum of 0.3 comma B2. And B3 is minimum of S3 comma B3 or minimum of 0.7 comma B3. Now we can calculate it pretty straightforward. So we'll take it in. So this is our B1. So B1 dash would be minimum of 0.3 and 0.1, 0.1, minimum of 0.3 and 0.4, 0.3, minimum of 0.3 and 0.1. And therefore, right? And in order to obtain the final output, we perform the maximum aggregation of this local output fuzzy sets, right? That is, you take the row wise column. So what would be B dash? It would be zero point 0.5 y1, it would be 0.5 y2, and you have 0.3 y. So this is your output fuzzy set when you are given this rule base of three meso rules, and these meso rules happen to be disjunctive in nature, and your out input fuzzy sets were A1 dash and A2 dash. Now we can have a case where some rules, some meso rules are disjunctive and some are conjunctive. So for example, consider this rule base. So the first rule and the third rule is disjunctive, you have or, and the second rule is conjunctive because you have an and. So let us do the inference in this case. Again, this we have already computed 0 0.3, 0 0.3, 0 0.7, 0 0.2, 0.2, 0.2. So first rule is disjunctive, so we'll take the maximum, so we'll get 0.3. Second one is conjunctive, so we take the minimum and we'll get 0.2. Third rule again is disjunctive because we have an or, and therefore you will take the maximum and we'll get 0.7, right? And therefore, what will be your B dash? Right? So in order to obtain B1 dash, we'll take minimum of 0.3 with B1. So that would give us 0.1, 0.3, 0.3. In order to obtain B2 dash, we'll take the minimum of zero point 0.2 with membership values of B2. So that will give us 0.2, 0.2, 0.2. And in order to obtain B3 dash, we will take minimum with 0.7, with minimum with zero point 0.7 of membership values of B3. So 0.5, 0.5, and 0.3. And in order to obtain the final output B dash, we simply take the maximum of B1 dash, B2 dash, and B3 dash, which is nothing but row wise score. Excellent. Okay. So this is the inference you get when you have a rule base, meso rule base of meso rules where some are conjunctive and some are disjunctive. Okay. So with this, we are done with the Mamdani inference part. And more broadly, we are done with conditional and unqualified fuzzy propositions, namely propositions of the form if X is A, then Y is B. We saw how to compute their truth values. We saw how to do inference with them. There are two broad paradigms, CRI and SBR, compositional rule of inference and similarity-based reasoning. We also looked at generalized modus ponens based on these paradigms and generalized modus tollens. We also had a discussion on generalized hypothetical syllogism. And then we talked about Mamdani inference, which is an example of SBR. And it can also be looked from the lens of CRI, as I discussed. And then I considered the case where you have more than one rule and different kind of rules. So this type of proposition, conditional and unqualified proposition, basically formed the extensive major part of our discussion. Now the third type of proposition is unconditional and qualified. So unconditional means you don't have an if-then part. So no if and then, but you have qualification, which means you'll have a truth qualifier. So truth qualifier like very true or fairly false. So a couple of examples of unconditional and qualified fuzzy proposition. Fatima is tall is very true. The room is warm is fairly false, right? So you have a fuzzy proposition. Why fuzzy? Because we have vague concepts involved, concept like tall and warm, but there are no if and then thing, if and then here, and therefore they are unconditional. But we have a truth qualifier, very true, fairly false. So such propositions are unconditional and qualified. So As I mentioned, such truth proposition involve truth qualifiers, and truth qualifiers are terms like very true and fairly false, and they help us express more nuanced version of truth, right? So what it means to be true is different from what it means to be very true. I hope everyone will agree when I say that, right? So we can have more nuanced versions of truth that can be expressed by terms like very true, somewhat true, fairly true, and so on. Okay. And truth qualifiers are linguistic terms that enable us to achieve that. The canonical form of propositions of this type, propositions that are unconditional and qualified, is V is F is S, where V is a variable that assume value in some universal set capital V. F is a fuzzy set over this set V that expresses some fuzzy predicate, and S is a truth qualifier. So this is the canonical form. V is F is S. So let us take the first example, Fatima is tall is very true, and figure out what V, F, and S are. So Fatima is tall is very true. Pretty obvious that the variable V is height of Fatima. And this variable take values in the set of all possible human heights, which form our universe capital V. So from 50 to 210 centimeter. Fuzzy set F is basically the fuzzy set tall, right? It is a fuzzy set over the set of all possible human heights, modeling the wave concept tall. Okay, so that's our F. And what is the truth qualifier S? Pretty obvious, very true. Okay. Now let us consider another example. The second example that we started with. The room is warm is fairly false. So again, the variable would be temperature of the room, and it will take values in the universe capital V, which is the set of all possible room temperature. So maybe minus 50 to 50 degrees centigrade. What is the fuzzy set F? It's a fuzzy set over V, the set of all possible room temperatures that models the wave concept warm. So that's what our F is. And what is the truth qualifier? It's fairly false. Okay. So now the question is, how do we compute truth values of such propositions? Unconditional propositions where you have a truth qualifier. Now, Jade, and all things go back to Jade, right? So what Jade suggested that truth qualifiers can be modeled as fuzzy sets over unit interval, right? So unit interval is our set of all possible truth values, right? And he suggested that very true, fairly true, somewhat true, these truth qualifiers can be modeled as a fuzzy set over this set of all possible truth values, namely the unit interval. So, namely, given a truth value A, the extent to which it belongs to very true is A squared. Similarly, fairly true, it's A square root of A, right? So, if proposition P is true to extent A, then the truth value of proposition P is very true can be obtained by squaring the truth value of proposition P. And this kind of makes sense, right? Because very true is a more restrictive concept than being true. If a proposition P is true to degree, say, zero point 0.9, then it is very true to a degree less than zero point 0.9, right? Because very true is a more restrictive concept. It's a more demanding concept. It's a more narrow concept, right? And therefore, when you square it, zero point 0.9 becomes 0.81, right? And which aligns with our intuition that if a proposition is true to degree zero point 0.9, then it should be very true to a degree certainly less than zero point 0.9. In this case, it is 0.81. Similarly, fairly true is a more flexible concept. It's a more dilated concept. It's a more broad concept in comparison to uh, simply true, right? So if a proposition is true to degree zero point 0.9, then it should be fairly true to a higher degree, say 0.95 or 0.98 or 0.98. And that is achieved by taking the square root of zero point 0.9. Okay. And of course, absolutely true is a very restrictive concept. It makes sense only when your proposition is true to degree one. In all the other cases, it does not make sense to call our proposition absolutely true. And therefore, if your truth value is a equals to one, then we say that it is absolutely true. In all the other cases, we say that it's not absolutely true at all. Okay. And similarly, very false, fairly false, and absolutely false. Okay. Therefore, if we have an unqualified proposition P, then the truth value of P is very true is obtained by squaring the truth value of P. Similarly, truth value of P is fairly true is obtained by taking the square root of the truth value of P. Similarly, truth value of P is fairly false is obtained by 1 minus square root of truth value of P. Okay. So by modeling truth qualifiers as fuzzy sets over the unit interval here being seen as the set of all possible truth values, we have now developed the machinery to compute truth value of propositions like P is very true, P is fairly false, P is absolutely false, and so on. Okay. Therefore, now we were interested in finding out the truth value of the and an unconditional and qualified fuzzy proposition. The canonical form of such proposition is this: V is F is S. Now, if this truth qualifier was not present, then we know how to compute the truth value of P. Given a specific value for the variable V, the truth value of P would have been similar, basically the membership of V in the fuzzy set F. Okay. So this would have been the truth value of proposition P had there been no truth qualifier, but we have a truth qualifier. And therefore, we simply apply S to it. And that is enough. Okay. So I hope this is clear. And therefore, for our example, Fatima is very true. Fatima is tall is very true. The truth value of this proposition given a specific height h would be very true applied to truth value of this part. And that is basically the membership of h in the fuzzy concept tall, in the wake concept tall, which is which is basically fuzzy set tall. And very true is modeled by square function. So we get square. Similarly, the room is warm is fairly false. The truth value of this expression is obtained by applying the truth qualifier fairly false to truth value of the proposition you would have had if there were no truth qualifier. So the room is warm, which is nothing but the membership of temperature T in the warm fuzzy set. And this is nothing but or zero point 0.5, right? So given an unconditional and qualified truth proposition, we can compute its truth value. And this is the most we can do given such a proposition, right? After all, there are basically such a proposition just specifies something about the world. It does not express any conditionality. So we can't do any inference from them. All we can do is compute their truth value given certain value of input, right? Given the height of Fatima or given the temperature of room. Okay, so this concludes our discussion on unconditional and qualified fuzzy proposition. So the last part is conditional and qualified fuzzy proposition. So this is, in a sense, the most complicated type of fuzzy proposition. So a couple of examples of propositions of this type. If temperature is moderate, then fan speed should be medium is fairly true. If humidity is high, then AC temperature should be high is fairly false. Is very false, not fairly false. Sorry. So conditional, we have a conditional part in such proposition, which means we have an if and then, and we have a qualification here. So we'll also have a truth qualifier. Okay. So the canonical form of propositions of this type is if X is A, then Y is B. This is basically the conditional part. And then you have a truth qualification part, which is S. And variables X and Y take values in universal sets capital X and capital Y respectively. And A and B are fuzzy sets over X and Y respectively, expressing fuzzy predicates, right? And S is a truth qualifier. So this is not hard to recognize, right? So let us identify these variables X and Y and sets A and B and fuzzy this truth qualifier S for this couple of examples. If temperature is moderate, then fan speed should be medium is fairly true. So what is the variable X? It's nothing but the temperature of the room, assuming the context is rooms here, right? We are stating this rule in the context of a room. So your variable X would be the temperature of room, and it will take values in the set of all possible room temperatures, right? So many from minus 500, minus 50 to 50 degrees centigrade. So that is our universe capital X. And what will be fuzzy set A? It will be a fuzzy set over X modeling the wake concept moderate. Okay. What is variable y? Again, fan speed. So it is the speed of fan. It will take values in the set of all possible fan speeds, so maybe 0 to 700 RPM. And what would be fuzzy set B? It will be a fuzzy set over universe Y, modeling the wave concept medium fan speed, right? And what is the truth qualifier? Fairly true. Okay. Now, for the second example that we considered, if humidity is high, then AC temperature should be high is fairly false. Again, variable X is the humidity percentage in the room. So we need a way to measure humidity, right? And the general way to do that is uh, specifying in terms of a percentage, right? So X is the humidity percentage in the room, and this will take values in the set of all possible humidity percentages, and that will nothing, of course, be that will be 0 to 100, right? Because that's where the percentages lie. And what will be the fuzzy set A? It will be a fuzzy set over the set of all possible humidity percentages, expressing the vague concept of high humidity, right? Now notice that I have specifically written high humidity instead of just high because we have high in both the antecedent and consequent part. And therefore we needed a way to distinguish between high humidity and high temperature. And that is why I've used the full like term high humidity. And what will be the variable y? AC temperature of the AC. And it will take values in the set of all possible AC temperatures. So from 16 to 28 degrees centigrade. In fact, it should be a discrete set, right? Because in an air conditioner, we are not allowed to set the temperature to 16.5 or 16.7, right? It's a discrete set. So my bad. So it should have been this. And B is a fuzzy set over Y expressing modeling the wave concept of high temperature. Okay. And our truth qualifier is of course fairly false. Okay. Now the question is, given a conditional and qualified fuzzy proposition, how do we compute its truth value? Now, if this is S part was not in P, then things would have been easier for us. We already know that a conditional fuzzy proposition, that is, if X is A, then Y is B, expresses a conditionality between variable X and variable Y. This conditionality is captured using a fuzzy relation R from universe X to universe Y. This relation R is built using a fuzzy implication. And this relation R essentially gives us the truth value of the proposition given a specific value of input variable X and output variable Y, right? But so we know the truth value of this part. It is given, of course. Now we have a truth qualifier as well. So this is if this is our P naught, then P is basically P naught is S, or P naught is very true, P naught is fairly false, and so on. And how can we compute the value of truth value of P from P dash? Simply apply the truth qualifier S to the truth value of P dash. That is S of, okay. The idea is very simple. We look at P without the truth qualifier is S. And in that case, we know how to compute the truth value. It's nothing but the value of the relation R at X comma Y. But since you already have a truth qualifier S, you'll have to apply S to it. Okay. We have already seen that if you know the truth value of proposition P dash, then you can compute the truth value of P is very true by applying very true to truth value of P dash. Similar now, instead of very true, we have a general truth qualifier S, so we apply S to it. Okay. So the truth value of P is modeled using a fuzzy implication I and expressed as a fuzzy relation R from X to Y, given in this particular manner. You know, this is nothing but the relation you would have had if this truth qualifier was not present. But we have this truth qualifier, and therefore our relation R becomes this. Okay. And given a specific value for input and output variable, you can compute the truth value of proposition P like this. Okay. Again, nothing very complicated. Just look at the conditional part. We know how to extract a fuzzy relation from it. It's nothing but I of mu ax comma mu by, and just simply apply the truth qualifier s to it to obtain the relation corresponding to p. And that relation R essentially is what gives you the truth value. Okay. So for the particular example that we started with, if we know that the temperature is 35 degrees centigrade and fan speed is 200 RPM, then what will be our truth value? It would be fairly true at I of mu a 35 and mu b 200, right? But fairly true is modeled by the square root function, and therefore this is what you get. Okay. If humidity is high, it's fairly false. Fairly false is modeled by 1 minus square root. 1 minus, okay, so this is fairly false, right? So 1 minus square. Wait, I think fairly false is modeled by, just a minute. Of course, it's square root, right? This is a typo here. Oh, sorry, it's very false, right? I should be a bit careful since truth qualifier is very false. So this, of course, should be 1 minus square function. So in other words, when you are given that the humidity is 80% and AC temperature is 20 degrees centigrade, you apply the truth qualifier 1 minus square to the relation that you would have gotten if there were no truth qualifier, right? So in other words, when you just had this property. So we saw conditional and qualified fuzzy propositions. We looked at their canonical form. We did a couple of examples, and we also saw how to compute the truth value. But as is indicated earlier, a conditional proposition expresses a conditionality between x and y, between input variable and output variable. And therefore, given a particular value of input variable, we want to express conditionality to infer a particular value for the output variable, right? That is simply doing the truth value computation for conditional and qualified fuzzy propositions is not enough. We want to do more. Namely, we want to do inferencing. More specifically, given a conditional and qualified fuzzy proposition, if x is a, then y is b is s, we want to, and a particular input fuzzy set a dash, we want to infer an output fuzzy set b dash, right? Now we have already seen how to do this with conditional and qualified fuzzy propositions. We had a very extensive discussion covering so many different cases. Now the question is, how do we deal with conditional and qualified? How do we do inference with conditional and qualified fuzzy propositions? And one method that is proposed in literature to do this is the method of truth value restriction. Now, this method of truth value restriction is somewhat complicated. And generally, in books, you will find that the author just lists the 4 steps that are involved in this method of truth value restriction. And hardly you get a explanation of why those 4 steps are defined the way they are defined. So, what I want to do in the last few slides is try to explain to you why those 4 steps are defined the way they are defined. Okay, it's not going to be easy because those again the steps are a bit complicated, right? But once you take some time and go through them again and again, things become clear to you, right? And what I want to do is like convince you that that is the case. Okay, so let's take that arduous task. We have a conditional and qualified fuzzy proposition. That is, we have if x is a, then y is b is s. X and y are input or antecedent and consequent variable respectively. They take values in universal sets capital X and capital Y. A and B are fuzzy sets over X and Y respectively, and S is a truth qualifier. Now, given an input fuzzy set X equals to A dash, we are interested in inferring Y equals to B dash. Okay. Now, as the in when we are dealing with just conditional fuzzy propositions that were not qualified, that is rules of the form if x is a then y is b, then we saw two methods, compositional rule of inference and similarity based reasoning, broadly like two paradigms. And in both those two paradigms, you were inferring the output fuzzy set, right? So you were inferring the output fuzzy sets directly. Or in other words, those methods are fuzzy sets driven. These are fuzzy sets driven. The method of truth value restriction, on the other hand, as the name itself suggests, this is truth value driven. Okay. And therefore, we express our conditional and qualified fuzzy proposition or a qualified if then rule in this form. If P then Q is S, where P is the antecedent proposition X is A, this is P, and Q is the consequent proposition, namely Q is P. And S is, of course, our truth qualifier. So to repeat, method of truth value restriction is truth value driven, as the name itself suggests, right? And therefore, to focus only on the truth values, we express this if then rule in the form of if P then Q is S. P is our antecedent proposition, X is A, Q is our consequent proposition, Y is P. And in this truth value restriction, method of truth value restriction, which we're going to abbreviate as TVR, we have 4 steps involved, as I alluded to earlier. So in the first step, we ask ourselves the following question. How true is the antecedent proposition, that is proposition P, X is A, given the fact that X is A dash, right? Because we have this rule and then we have the input fuzzy set X equals to A dash. So that's a fact that is supplied to us. And therefore, in the first step, we ask ourselves the question, how true is this antecedent proposition X is A given the fact that X is A dash? So this is the question that we will answer in the first step. Now, suppose instead of this question, we had a fairly simple question that what is the truth value of P given a specific value for the input for the variable X. So say X naught. Then we already know that this is nothing but the membership of X naught in A, right? So this is the most simplest type of X is A. This proposition is basically an unconditional and unqualified fuzzy proposition by itself. And that's the most simple kind of fuzzy proposition we can hope for. And the truth value of such a proposition given a specific value, say X naught of X, we know that it is nothing but mu A X naught. In other words, this membership function of fuzzy set A acts as a truth value evaluator, or in simple terms, truth evaluator of proposition P, right? Given different values for input variable X, I can simply substitute it in the membership function and that will give me the truth value of proposition P. So that membership function mu A acts as truth evaluator of proposition P, right? Now, mu A as a function is a function from X to unit interval. Now, we are interested in this question. How true is P given X is A dash? So X, instead of assuming a specific value X naught, assumes a fuzzy set A dash as value, right? Because the fact that is supplied to us is X is A dash. So our variable X, instead of assuming a specific value X naught, which is the most easy case we can hope for, it assumes a fuzzy set A dash as value. And then we are interested in finding out how true the proposition P in light of this given fact. And we have seen that the membership function of A acts as truth evaluator. But this is a map from X to 0, 1. So given an X naught, we can compute mu A X naught and that will give me the truth value of P. But now X naught, instead of assuming a specific value x naught, x has assumed the variable x has assumed a fuzzy set as a value. That is, it has assumed a value in fx. Now, how do we deal with it? What to do in this situation? We will simply apply the extension principle to our membership function of it. Membership function is a function after all. It's a function from x to unit interval. It acts as truth evaluator of P in cases the variable assumes a specific value x naught. In our case, x has assumed a fuzzy set as a value. And to be able to extend this truth evaluator to that setting, we simply use the extension principle. When we apply extension principle to this function, what we will get? We will get the extension of mu a to f of x, basically fx, the fuzzy power set of x. Again, what I'm saying may not make immediate sense, but try to follow. We are extending mu a using extension principle, and that will give me, say, mu a cap, right? And this mu a cap is a function from fuzzy power set of x to fuzzy power set of unit interval. And what will be the membership of this? And thus, given the fact that x is a dash, that is x is a dash, I can evaluate this mu a cap on it, right? Right? And that will be a member of this, or in other words, that will be a fuzzy set over 0, 1. Right? So let us call the membership function of the fuzzy set that we get when we apply this function mu a hat on a dash be rt of a dash by a. So if we just follow the notations that we have, then we will have mu a of e dash. So this is a fuzzy set over 0, 1. And then when we write the membership function of this fuzzy set, we will have something like this. This is a very complicated notation, right? So I'm ditching that and I'm using this as the notation, right? So to summarize, mu a, the membership function of a, acts as the truth evaluator for our proposition P when the variable x assumes specific values. But we are faced with a situation where the available fact is x is a dash. The variable x, instead of assuming a specific value, assumes a fuzzy set a dash as value. So what to do in such a case? We extend our truth evaluator, which is the membership function of a, using extension principle to f of x, right? And when we apply extension principle to this function, we get mu a cap, and that is a map from fuzzy power set of x to fuzzy power set of unit interval. And therefore, given x equals to a naught, I can evaluate this extended truth evaluator on a dash, and that will be a fuzzy set over the unit interval. And I'm calling the membership function of that fuzzy set to be rt of a dash by a. Why I'm using the term rt will become obvious in a few minutes. Okay. So mu a can be extended using extension principle to act on fuzzy subset of x dash, right? And given a dash, we can compute this, and this will be a fuzzy set over unit interval, right? And this is basically the membership function of this set. Okay, I'm using this symbol for clarity, for the sake of clarity, and for implying something that will become obvious. Okay, so what will be the definition of this? So remember, when you have a function from x to y and you apply extension principle to it, you get f cap, which is a function from f of x to f of y. And given a fuzzy set a over x, your f cap of a is a fuzzy set over y. And how this f cap of A is given? It's the supremum of mu ax, and the supremum is carried over all x in the universe such that f of x equals to y. Okay, so this is the definition of extension principle. I'm just applying that in this setting. What would be the membership of A in this fuzzy set? It will be nothing but supremum of mu A dash x, where supremum is carried over all x such that mu ax is equals to A. Take some time and recognize. And this is how the membership function of this looks like. Now, this RT of A dash by A, what does this denote? Right? Maybe it will help to go back to our original question. We were interested in finding out how true is the antecedent proposition P x is A given the fact x is A dash. Now, we were expecting to get a specific truth value as the answer. How this is true to extent 0.4 or 0.9. But what we have ended up achieving is a much more nuanced answer to this question. Instead of giving a specific truth value as the answer, we are saying that we have built a truth profile. We are saying that you give me a truth value A, and I will tell you how confident I am that this proposition Px is A is true given the fact x is A dash to extent A. Okay. So this RT of A dash by A, instead of giving specific truth value as the answer to the above question, gives a truth profile for P given x is A dash. That is, it tells you RT given a particular truth value A, RT of A dash by A at A, it tells you what is our confidence or how confident we are that P, our antecedent proposition P, x is A, it is true given to degree A. Okay, take some time and recognize this. Instead of giving ki ha bhai, this proposition is true to a specific truth value, we are suggesting a much nuanced thing. We are saying ki for any truth value, I can tell me how confident I am that this proposition is true to that particular truth value. Okay. Or another way to state this is that RT of A dash by A of A tells me that P is true to degree A is supported by the fact that x is A dash to this degree. Okay. So I will quickly summarize. In the first step of the PVR, we are interested in how true is our antecedent proposition x is A given the fact that x is A dash. When we dealing with a very simple case when x was assuming specific values from the universe, truth value of P was fairly straightforward to compute. It is nothing but membership of x naught in A. Or in other words, the membership function A acts as truth evaluator of P. Now we are faced with a situation where instead of assuming a specific value, the variable x assumes a fuzzy set A dash as the value. Then how do we compute the truth value of P? So by using the fact that mu A, membership function of A, essentially acts as truth evaluator, we can extend the mu A using extension principle so that it can act on fuzzy subsets of X. And when we do that, we end up getting a function mu A cap. And we can apply mu A cap at A dash. Right? And that will be a fuzzy set over the unit interval. I am denoting the membership of that unit of that fuzzy set by RT of A dash by A. Right? And when we look at the when and this RT by A dash by A answers our original question, and it gives a much more nuanced answer to it. It tells me, given any truth value A, how confident we are that antecedent proposition P is true given the fact x is A dash to degree A, that particular truth value. Right? In other words, RT of A dash by A acts as a truth profile. Okay, that's the term I have used. It gives a truth profile for P given X is A dash. Okay, and if you're not very convinced that this makes sense, maybe the next example will give you some idea. So suppose I take a proposition X is good. Suppose this is our antecedent proposition P, right? Where variable X is basically the name of a song, the name of songs, and good is a fuzzy set over, and this X, the variable X is the name of a song, and suppose it take values in some music base S, maybe the music base of Spotify or Geo Music or whatever app you use. And good is a fuzzy set over that music base prepared by some music critic. And this fuzzy set good captures to what extent a given song is good. That is, given a song X, mu good of X, which is some number in the unit interval, tells us to what extent song S is good as per the music critic, right? The music critic who has prepared this fuzzy set good. Now, music critique, or for that matter, uh, art critiques in general, have a reputation of being self-indulgent. They'll say that a particular piece of music is a masterpiece or a particular movie is a masterpiece, and you actually go to a cinema hall or a concert to listen to that music or that watch that film, and it turns out that it is decent at best. It's certainly not a masterpiece, right? So it is very natural for me to check if I agree with this music critique. So what will I do in that case? I'll prepare my own fuzzy set good for good songs, and I'll call it good dash. So good dash is again a fuzzy set over the music base X, and for song X, mu good dash of X is the extent to which I consider the song X to be good. Okay, so this fuzzy set good dash is the fuzzy set that I have prepared. Now this RT, right? So basically, now what we are interested in, to what extent this proposition X is good is true given X is good dash. So initially we had just one proposition, X is good, right? It that proposition helped us figure out to what extent different songs are good, right? And I hope that is obvious, right? Because given a particular song X, truth value of P is nothing but the membership of X in the fuzzy set good, which is the fuzzy set prepared by the music critic. So this proposition P helped us figure out to what extent different songs are good, and this was this and the way we are doing that is using is by the help of some music critic, right? Now what? Now we are very. It is very natural to us to what extent this proposition P is true. Now that I have my own fuzzy set for good songs, that is to what extent P is true given X is good dash, right? So I hope the setup is clear to you. We have a proposition X is good that help us decide how good different songs are, but music critics are unreliable, and therefore I prepared my own fuzzy set, good dash. So therefore now we have a new piece of information. We have a new piece of fact that X is good dash. And then we are interested in finding out to what extent P is true given this new fact X is good dash. And that is what RT good by good dash answers. It tells me how much I agree with the critics' different level of ratings. So suppose I take a particular rating value 0.9. Okay. Then given a song X, if it so happens that membership of X in fuzzy set good is 0.9, then that means the music critic considers the song X to be good to extent 0.9, or the music critic has assigned 0.9 good rating to song X. Now I want to figure out to what extent I agree with this zero point 0.9 good rating of music critic. Now, from the formula of RT that we have already seen, this is what we will get. And this makes perfect sense. Why? Because we are first finding out set of all x such that mu good of x is zero point 0.9. That is, we are first of all finding out all the songs that the music critic considers to be zero point 0.9 good. And in that pool of songs, I am taking the song that I considered that I give the highest rating, right? I'll repeat. We are first considering set of all x such that mu good of x is zero point 0.9. That is, we are looking at all the songs that are rated zero point 0.9 good by the music critic. And in that song, in that pool of songs, we are taking supremum of mu good dash of x. Or in other words, in that pool of songs that are 0.9 good rated by music critic, I am taking the the highest rating I have given to a song in that particular pool as my level of agreement with the critic's zero point 0.9 good rating. And this makes sense. I have to decide how much I agree with the particular music critic's zero point 0.9 good rating. So I look at all the songs that he considered to be zero point 0.9 good. And in that particular pool of songs, I'll simply take the song that I consider that I have given the highest rating, and that rating can be considered as a level of agreement of my level of agreement between me and the music critics zero point 0.9 good rating. Okay. So I hope this example convinced you that this RT of A by A dash by A essentially tells you how good, not how good, how true P is given the new piece of fact X is A dash. Okay. And that is why this RT of A dash by A is also called as the relative truth value of A dash with respect to A. And that is why I use the letters R and T. RT stands for relative truth. Okay. So the first step was the most complicated step, I would say. Computationally, it's fairly straightforward, but the meaning behind it is somewhat difficult to decode. So in the first step, we compute the relative truth value of A dash with respect to A. This tells me how true the antecedent proposition P is given the new fact X is A dash. And this RT.AS gives a truth profile for this question. It basically tells you what is our confidence that P is true given X is A dash to extent A. Okay. Now, having performed the first step, in the second step, we look at our conditional if then rule that is given to us. If P then Q is S. Now, this is a qualified conditional rule, right? And since we have an if and then, we have this proposition expresses a conditionality between proposition P and proposition Q, right? And that conditionality is captured using a fuzzy relation T. But this is a fuzzy relation not from universe X to universe Y. Remember, here we have proposition P and proposition Q, right? And if P then Q expresses a conditionality between truth value of P and truth value of Q. Therefore, our fuzzy relation T would be a fuzzy relation from the unit interval to unit interval. Unit interval here being the set of all possible truth values. Okay. And here you can see the distinction between method of truth value restriction and CRI or SPR. Okay. So we build our this relation T that help us capture the conditionality expressed by the given conditional and qualified rule like this. Okay. So if given that P is true to extent A and Q is true to extent B, to what extent if P then Q would be true? It would be true to extent I of A comma P. And we also have a qualifier, so we'll apply S to it, right? So therefore, this conditionality expressed by the given conditional and qualified rule is captured by this fuzzy relation R, which is a fuzzy relation from set of all truth values to set of all truth values. And this is how it is defined for all truth values A and B. So our second step was that. In the third step, we ask ourselves the following question. We started with what? We started with this conditional and qualified rule, right? And an additional piece of fact that X is A dash. And our goal was to infer that Y is B dash, right? And we translated everything in terms of truth value, right? So if P then Q is S, okay, right? In the third step, we are asking ourselves the following question. How true is the consequent proposition Q, which is basically nothing but Y is B, how true this consequent proposition is given the fact, given this rule that we have, or equivalently this rule, and the fact that X is A dash. Okay. This is kind of similar to the first rule, except for the fact that when we are talking about how true the consequent proposition P is, we not only have X is A dash as our as the piece of information, but also the fuzzy if then rule, right? Now, how do we answer this question? Now we know that relative truth value of A dash with respect to A is a fuzzy set over the unit interval. And this gives me a truth profile that help us answer the question how true the antecedent proposition is given X is A dash. And we know the conditionality that between truth values that is expressed by this rule, if P then Q is S, is given by this relation T. Now, if we compose both of them, I'll get a fuzzy set over the again the unit interval. And that fuzzy set will give me a truth profile that help us answer this question. That how true is the consequent proposition given the fuzzy if then rule, if P then Q is S, and the fact that X is A dash. Take a moment and digest this. This tells you how true the antecedent proposition is given the fact that X is A dash. This state captures the conditionality if P then Q is S, right? And then we are finally interested in the question that how true is Q given this fuzzy if then rule and the fact that X is A dash. Now you already know the truth profile for the antecedent proposition and you know the relation that captures this truth value conditionality. So you simply compose them and that will help you give us a truth, that will help you obtain a truth value profile for the proposition Q, which is the consequent proposition given the fuzzy if then rule and the fact that X is A dash. Okay. And what will be the expression for this RT A by A dash compose B? And by the way, this truth profile of for that help us answer this question, how true is the consequent proposition given the fuzzy if then rule and the fact that X is A dash, is precisely the relative truth value of B dash, the fuzzy set that we infer with respect to B, right? We started with this setup, right? We have a conditional and qualified if then rule, and we have a additional piece of information, namely X is A dash. And using these two pieces of information, we wanted to conclude Y is B dash, right? So B dash is what the inferred set is. And this proposition, this question that we asked, that we answered using this composition, it is nothing but the relative truth value of B dash with respect to B, right? That is RT of B dash by B is nothing but the composition of RT of A dash by A with this relation T. And if you write down the formula, this is what you will get. We have a composition, so maximum composition. So you will have supremum over A in the unit interval and minimum of RT A dash by A of A and T of A comma B. And T of A comma B we already know is S of I of A comma B. Right? Now, generally in books you find this formula, but there is a whole line of reasoning behind it. So we are done with the first three steps. We are only left with fourth step. In fourth step, we recover our output fuzzy set B dash from this relative truth value. And how do we do that? So given a particular element Y from the universe capital Y, we are interested in finding out the membership of Y in B dash. Okay. Now we start by recognizing that what this, we first find out the membership of Y in B, that is mu by, and then we recognize that what exactly this mu by answers, what exactly this represents. Now, this represents the truth value of the consequent proposition Q, which is Y is B, given a specific value for the variable Y, right? Now, this is an unconditional, this is a very straightforward proposition, right? And we already know how to compute the truth value of such propositions. So given this Y is B proposition and a specific value for the variable Y, mu B of Y is nothing but the truth value of this consequent proposition. Okay, right? Then we have B dash by B, right? And for any truth value B, RT of B dash by B at B tells us how confident we are that the truth value of Q given the fuzzy if then rule So RT of B dash by B of B tells us how confident we are that the truth value of Q, given the fact if the given the fuzzy if then rule and the fact X dash is A is B, right? Okay. Now for a particular value of Y, we already know that mu B of Y is the truth value of the proposition Q is Y of B. And therefore, tells me how confident we are that the truth value of proposition P of the proposition Q is mu B of Y given the if then rule and the fact that X is A dash. This is the input given to us. Okay. And that is what, and that is how we define the fuzzy set B dash. And it makes sense to do that, right? Because all we have is a conditional and qualified fuzzy if then rule. And we have an additional piece of information X is A dash. From that, we are able to find out how true the consequent proposition Q will be given this rule and this fact that X is A dash. And at a particular value Y, we are able to compute the truth value of the consequent proposition. And therefore, we define the mu B dash of Y as the degree to which Q is true to mu by is supported by the fuzzy if then rule and the fact that X is A dash. Okay. Again, method of truth value restriction is not very straightforward. It takes plenty of time to digest all the four steps and recognize the semantics of them. So I would definitely not be disappointed if if you're not able to understand this now. I would suggest you to watch it again and again. Go to Google and do some Googling as well, and convince yourself that this is what goes on, right? This makes sense. Okay, so to summarize, method of truth value restriction involve four steps. First step may be evaluate this relative truth value of A dash with respect to A. In second step, we evaluate the fuzzy relation T, which help us capture the conditionality between the truth values of antecedent proposition and consequent proposition given the rule. In third step, we evaluate RT of B dash by in B. And in fourth step, we recover B dash. So these are the four broad steps. Now let us do a problem and be done with this discussion session. It has already taken a lot of time. So this is the conditional and qualified if then rule given to us. This is our fuzzy set A and B. And we have a truth qualifier very true. So recall very true is modeled as A square for all truth value A. Okay, so how will RT of A dash by A will be defined? So it's a fuzzy set over the unit interval, right? And how is it given? Sorry, this is not a fuzzy set over the unit interval. This is the symbol we are using for the membership function, right? So that's a distinction. Okay. Now we notice that the fuzzy set A only has three membership values. It attains three membership values, namely 1, 0.5, and 0.7. Therefore, for all A in the unit interval, except 1, 0.5, and 0.7, the set of all x such that mu ax is A would be empty, and thus the supremum of x coming from universe x such that mu ax is equals to A of mu a dash of x is nothing but the supremum of empty set, which is 0. So the only interesting cases are when A is equals to 1 and A equals to 0.5 and A equals to 0.7, right? So, so for that, we have to find out all x in the universe, capital X, such that mu ax is equals to 0.5. But that is the case for only x2. And therefore, right? And this is 0.6. Similarly, what is the value of RT A dash by A at 1? This is given by this. So we first find out the set of all x such that mu ax is equals to 1, but that happens only for x1. So therefore, this becomes sorry. Right? So we have calculated our set RT A dash by A. Fuzzy set RT A dash by A. Okay. Now, what will be our in second step? We will build our fuzzy relation AB, which is a fuzzy relation from 0. And we are said, okay, nothing is given regarding the implication that we are required to use. So say use Ukashevich implication. So Ukashevich implication, if you remember, is given in this manner. And S is very true, which is square, so it becomes minimum of. Okay. Now, so second step is done. Now we finally evaluate the third step. Okay. And third step is basically involves computing this, which is nothing but the composition of, right? So RT of B dash of B of E is supremum of, right? Now notice that RT of A dash by A is 0 for all A in the unit interval except 1.5 and zero point 0.7. And we can use that fact to observe something. We can break this supremum into two parts. First one where we carry out the supremum over 1, 0.5 and zero point 0.7. And in other, we carry out the supremum at the remaining points. But this is 0 at all A except 1.5 and zero point 0.7. And minimum of 0 and some number in the unit interval is again 0. And therefore, this whole thing would be 0. And this is basically maximum of some numbers in the unit interval. So this is supremum of minimum of these things. So basically, this quantity is going to be greater than equal to 0. And we are taking maximum of some number greater than equal to 0 and 0. So we are left with this part only. And we are taking supremum as A varies between 1.5 and zero point 0.7. So we are doing maximum only, right? When you take supremum over a finite set, it becomes maximum. So maximum of minimum R2 of um, okay. And now we can um, uh, our step 3 is done. In step 4, to be honest, you can now do further simplifications. You can consider different ranges for B and can compute a closed form expression for this thing. But I'm not interested in doing that because after all, we are interested in just inferring the output fuzzy set B dash, right? And we know that B dash is given in this manner, right? And membership function of B takes two values, zero point 0.6 and 1. Therefore, we are only interested in the value of RT of B dash by B at zero point 0.6 and 1. What it takes over other values of B, we are not really, that does not interest us, at least as far as this question is concerned. Okay. So phi 1 is and mu B of phi 1 is 0.6. Okay. And using this fact, we infer that this becomes maximum of minimum of zero point 0.9 comma 1.6, right? Minimum of. Now notice that RT of, I should have written this here only. This is zero point 0.9, this is zero point 0.6, and this is zero point 0.7, right? So this is zero point 0.9 only, this is zero point 0.6, and this is zero point 0.7. I hope I'm, yeah, right. Okay. So I'm just now computing this expression, RT of B dash by B at zero point 0.6. Right? And recall, so this thing will become what? 0.6 and zero point 0.6 square. So this becomes 0.36, right? And therefore this term, first term is 0.36. What is t of zero point 0.5 and zero point 0.6? It's 1 minus zero point 0.5, which is zero point 0.5. 0.5 plus zero point 0.6 is 1.1. Minimum of 1 and 1.1 is 1, and therefore its square is also 1, and therefore this is zero point 0.6. Similarly, this whole thing, tau of t of zero point 0.7 comma zero point 0.6 is 1 minus 0.7, 1 minus zero point 0.7, which is 0.3. 0.3 plus zero point 0.6 is zero point 0.9, right? And zero point 0.9 squared is 0.81, and minimum of 0.7 and 0.81 is zero point 0.7. So maximum of 0.36, zero point 0.6 and zero point 0.7 is zero point 0.7. Similarly, membership of Y2 in 1 is, this is 1, and therefore this becomes maximum of minimum of 0.9 comma 1 comma 1, minimum of 0.6 tau comma zero point 0.5 comma 1, and this becomes minimum of 0.7. What is this? This is 1 square, so 1 only. And what is this? This is again 1 square, so 1 only. This is again 1. So this whole thing is 0.9, 0.6, and 0.7. And therefore, this whole thing is 0.9. Thus, B dash is 0.7 y1, 0.9 y2. Therefore, given this conditional and qualified fuzzy if then rule, and using Ukashevich implication and this input fuzzy set A dash, the truth method of truth value restriction gives us this output fuzzy set B dash, 0.7 membership for y1 and zero point 0.9 membership for y2. So we are done with all the 4 categories of fuzzy proposition. So this took a lot of time, certainly more time than what I expected. But I wanted to give a sense of how things actually work instead of just explaining you the formulas, right? I wanted to sort of give you a more deep sense of how we deal with fuzzy propositions, what are their canonical forms, and we also had a discussion on that particular conditional and unqualified fuzzy proposition. If tomato is red, then it is ripe. That helped us get a sense of how to construct fuzzy sets in real life applications, right? So yeah, that's it for this part. Thank you very much.